Hello everyone, and welcome to this wonderful course of general mathematics. It's a course that's going to excite you, challenge you, and teach you a few new things. I'm particularly excited to welcome you to data and statistics. Like many of you, for a while I thought, this is not the most exciting part of the course. We sketch a few graphs, we count a few numbers, what's the big deal? But then, a few years ago, I had the opportunity to go overseas and begin working as a data scientist, which I've been doing for the past few years, working with machine learning to make predictions about the world around us and try and predict the future. General mathematics is the best course in the entire VCE. I was so happy that I'd taught it as a teacher because suddenly every day I was making 5-number summaries to predict things and understand the data. I was printing histograms for data sets with millions of pieces of data to be able to build a machine learning about it. I was having regular conversations about correlation and causation and whether what we were finding is actually something we can make a prediction from. And we were using time series to understand the past and try and work out what's going on in the future. Data science is one of the most in-demand jobs in the entire world and often ranks high in the lists of best jobs to work in. It's used in all the industries around us. Self-driving cars use data science and machine learning to predict and identify what's happening in an image. Netflix's recommendation algorithms are based on machine learning and data science to give you recommendations of what to watch. We're going to be looking a little bit later on at some of the data around climate change and understanding what's going on there. And these kinds of tools are used again and again in all of the industries. In health, to improve hospitals, to make diagnoses. And I was speaking to a friend who works at Jetstar the other day, and he said that they may or may not be using data science to predict which bags will go missing and which planes might not be on time. So the world needs data science. It needs you. As part of our learning in data science and data and statistics, I've prepared for us a bunch of real-world data sets. And a lot of the learning we're going to be doing is going to be based on some of the data that you see in front of you. Today, we're going to look through the triangle window at Titanic data. I have here a list of all of the passengers who were on the Titanic. There were 2,240 of them. And I've shown you just 4 rows of 4 people. We have for every single person on the Titanic, their name, the class that they were in, male, female, their age, ticket number, fare, and where they came from or where they were going to. We have more data as well, which we'll look at in future lessons. Did they survive or didn't they? Today, we're going to be looking at types of data, and we're going to use some of these real people to understand what's going on. 2 main skills in today's lesson: ordinal and nominal data, discrete and continuous data. These are things that you guys have probably come across before, but there might be some nuances that you'd like to clarify. Alrighty, so we know data is divided into 2 categories, our numerical data and our categorical data. Within numerical, we have discrete and continuous. Within categorical, we have ordinal and nominal. Let's dive into this detail a little bit more. We're now in the world of numerical data, which we divide into discrete and continuous. Discrete is data that we count. So how many times have you listened to Taylor Swift's Blank Space on repeat? Or continuous data is something that we measure. How far did Buddy Franklin stand from the goals when he kicked that ball against Port Adelaide? I can show you incredible things. And he might try for a 70-meter goal. Then he really would be worth all the money they're paying him. Give him a longer contract. Let's understand this a little bit more with some examples. Discrete, counted. Continuous, measured. The speed of a motorbike is something that we measure. It might be 56 kilometers per hour. The number of people in a classroom is something that we count. We can get 5, 6, or 7, etc., etc. But let me clarify this with a little bit more detail. When we're talking about discrete data, there are gaps in between. Between this number 5 and 6, I can't find anything in between it. But if I were to give you 2 speeds, 56 kilometers per hour and 56.2 kilometers per hour, you could find a number in between them, 56.1. If I gave 56.1 and 56.2, you could still find a number in between them, 56.15. And that can go on forever. If that can happen, then you're talking about continuous data. If you can't do that, then it's discrete. The weight of fruit, if I'm weighing something in kilograms, well, I could have 1 kilogram, 2 kilograms, but I could also have 1.5, 1.2, 1.25, 1.222. This is continuous data. The number of stars in the universe. This is often a tricky one because people think, oh, the number of stars go on forever. But actually, it's discrete data. The word continuous doesn't mean forever. It's talking about whether there are gaps or whether there aren't gaps. So I count 1, 2, 3, 4, 5 stars, 1,000,000, 1,000,001, 1,000,002. In between 1,000,001 and 1,000,002, there's no other number. So this is discrete data. Sometimes seeing a visual image can help us understand the difference between discrete and continuous data. Discrete data will always be represented with dots, 1, 2, 3, 4, whereas continuous data is shown with a line. And the line represents the idea that you always have something in between. If I look at 2.1 there and 2.15, I can find 2.134 in between. We're showing that you can zoom in as much as you want into that line and you'll always find something in between. Another important point to note is that discrete data can have decimals in it. So for example, let's say I was counting how many mandarins I ate every day, and I only counted it in wholes or halves. I said I could eat 1 mandarin, 1.5 mandarins, 2, 2.5. Then each of those numbers would be represented by a dot. And because I'm only counting in halves, there's nothing in between my 1.5 mandarins and my 2 mandarins. And therefore, that data that I'm giving you would still be discrete data, even though there are decimals in it. Another important point that can also cause confusion is that the context is really important when we're talking about the types of data. Someone comes along and says to me, is age discrete or continuous? I'd actually say, well, how are you measuring it? If you're counting it in years or in seconds and you're allowing as many decimal places as you want, that's continuous. I could be like, I am 102.325 years old, right? If we're allowing those kinds of measurements, then we are continuous. You could do it in seconds. I am 1,300,000 and blah, blah, blah seconds. And if you're allowing it to be represented with a continuous line, then that's continuous. But if someone said, I want to know your age in whole numbers of years, are you 12 years old? Are you 18 years old? Are you 72 years old? Then that is discrete. And even more so, if someone said, I want to know in just like in tags, like are you young or are you old? And that's not even numerical. Suddenly we're in the realm of categorical data. So this is why people often get confused, because the way the question is asked does actually impact the way you answer it. What kind of data is height? Now, usually I would say like this is something we measure, so height is continuous. And if someone just said to me, Tal, there's a gun to your head, are you going to call it continuous or not? Yeah, height is continuous. But if someone came along and said, how tall are you? Are you short? Are you medium? Or are you tall? Then that's no longer continuous. Suddenly that's categorical data. So I'm deliberately giving you some of the tricky kinds of questions because I want us to clarify the differences and the nuances in what we're studying. What type of data is a family's weekly spend on food? Go to the supermarket, you get your bill, you look at the number on that bill, receipt is the word we use here in Australia, and that number, what kind of data is it? So it's something that we're counting or measuring. It's numerical data. Why is it discrete? Because you can only ever have that given to you in cents. So what do I mean? You could be spending $20.12, $20.12, and you could be spending $20.13, but you would never spend anything in between. When you calculate your spend, there's nothing in between those. If I was to represent that, it would be given in dots, 20.12, and then another dot would be 20.13, and there is no dot in between. There's no line in between. So that's why it's discrete data. All right, we're now in the realm of categorical data, and categorical data can be divided into ordinal and nominal. Ordinal, from the word order, there's a certain order to what's going on. And nominal, from the word nom, meaning just name. In French, the word nom de plume, is like the pseudonym of an author, or nom de guerre is the like from guerrilla warfare, is the name of, it's the military name someone takes upon themselves if they're fighting a war and they want to keep their name secret. So nominal it's just the name. There's nothing like inherent about the value of them, whereas ordinal is there's a certain order to what's going on. Are each of these ordinal or nominal? Hair lengths, are you short, medium, or long? So that's going to be ordinal. because there's an order. Short comes before medium, which comes before long. Colors, red, blue, green, no order there. It's nominal. Postcodes. Now, this is a tricky one, and I've deliberately put it here because people often get confused with it. They see numbers like 3161, 3082, great spot, I actually taught there, and 3020, also a lovely place. And they say, oh, these numbers, they're numerical because they're numbers. But hang on, they're not things that we count. Like, I'm not counting, 3162 comes after 3161. They're just representing different areas, and they're not something we measure. The fact that they represent different areas means that they're categories, right? They're just names for different places that we use numbers to represent. So this is categorical data, and there's no specific order. Like 3162 is not better than 3161, la 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 la. You can debate about that if you want. So we call it nominal data. All right, your turn. Which of these is an ordinal variable? Country names, there's no ranking there. Different genders, also no ranking there. It's not like one comes after the other. Height, there is a ranking there, but it's numerical, so we're not in the world of categorical. Pizza size, they're categories, small, medium, and large, and medium is after small, before large. It has an order. Which of these is a nominal variable? This is ordered. This is numerical discrete. The first 100 names on a list of the wealthiest people in the world, those are categories. They're not things that we're measuring or counting, but they're the actual people. But because they're on the list of the wealthiest, from like the richest to the less rich, even though they're super rich, that's an order. So that's ordinal data. C, suburbs. This is nominal data. It's categorical and there's no specific order. Mill Park, I taught there. Elsternwick, I went to school there. Sunshine, got a great friend who taught there. And Wandillagong, a beautiful spot right near Bright in regional Victoria. I was once at the Wandillagong pub, and a guy comes up to me and says, "Where do I know you from?" All right, we're calling this a mega Q activity. It's one question that summarizes all the different things that we've learned in today's lesson. Give it a shot. All right, let's go through each of these features, each of these columns, and understand which type of variable each one is. Name. Name is categorical nominal data. That's pretty clear. Class. This is an interesting one, okay? It is numbers, but we're really just talking about first class, second class, and third class. It's kind of like the suburbs, but like the postcodes, but this categorization of people into rich and poor, into first class and second class, does have an order. So it's ordinal data. Categorical ordinal. Sex, as measured at the time when they were getting people onto the Titanic, that's categorical and it's nominal. There's no specific order to it. Age in years. Now we're saying, how old are you? How old are you? And we're counting it. Something we're counting, that's discrete data. Ticket number. Another example of numbers, just like those postcodes. Those numbers are not measured or counted. They're just representing the different tickets that you have. So that's categorical, and it's also nominal because there's no specific order to it. We're not saying one is better than the other or that a big number represents something different to a smaller number. Fair, we can see it's dollars and it's measured in whole numbers of dollars. We're counting those, that's discrete. And our home or destination, where are we coming from, where are we going to, that's nominal. They're places and there's no specific ranking to them. So let's look through our options and let's work out which is false. There are 3 categorical nominal variables. 1, 2, 3, 4. That is false, my friend. Let's just check the others. Class is categorical ordinal. Yeah, that's true. 2 numerical, discrete, discrete. That's true. There are no continuous variables. That's true. Answer A. In all of our lessons, we're going to have a summary slide at the end to give you the key takeaways and ideas from the lesson. You're welcome to print these off and chuck them into your notes. Today's summary is nice and clean. It's a lovely tree that splits our categories. I will see you next time for displaying and describing categorical data. Gimme a mean or a median. Come and learn some data and statistics today. Today we're going to be looking through the oval window at our Netflix data. I have accessed a data set of over 5,000 titles that were on the US Netflix in about 2022. We have in this data the name of each type of show. Was it a movie? Was it a TV show? Taxi Driver, Monty Python, a bunch that I don't recognize. When it was released, the description, the rating, the runtime, and all these wonderful things. And if you're a data scientist, you get given a whole set of data, and you got to try and make some meaning of it. IMDb scores. We're going to look at this a little bit later on in chapter 2 to try and see if there's a connection between the type of title, whether it's a movie or a TV show, and whether it's liked more or less. But for now, we're going to be just exploring the data and getting a sense of what's going on. Displaying and describing categorical data. There shall be 3 key skills in today's lesson. One-way data, representing them in frequency tables and bar charts. Then representing that same data using a segmented bar chart. You'll see what that means soon. And then writing a report on categorical data. One-way data. One way or another. All right, we're going to look here at a frequency table that represents this one-way data. Why is it called one-way data? Because it's one variable. What's this variable? It's Netflix genre. And you're like, well, one variable, but lots of rows. How does that make sense? Well, this variable genre can take on lots of different values. It can be a drama. The genre can be a comedy. The genre can be documentary. Some of the ones that we're not seeing here are sci-fis and romances and a whole bunch of different other ones as well. In a frequency table, we count how many times each of these values of the variable genre occur. So there were 1,432 dramas, there were 22 westerns, and there were 4 sport titles out of a total of these 5,800 titles that I accessed. Let's see if we can analyze it a little bit. To help analyze, I've grouped all of the genres that weren't drama, comedy, or documentary into an other category, just so we have a little bit less data to work with. You can see there's a whole bunch of them, and that's okay. Looking at these numbers, sometimes it's hard to compare, and a way that can help us compare more easily is to calculate the percentage frequency. 50%, 70%, 20%, that'll help us understand a little bit more about how much these genres represent of all the figures. How do we calculate percentage frequency? There's a nice little formula here if you want to see. But basically, we count the frequency. So let's do the percentage frequency of the dramas. 1,432. It occurred out of 5,806 titles. That would give us a decimal, so we times it by 100 to get the percent. And it gives us 24.66%. In this table, we're doing them rounded, so 25%. And you can see that all of the percentages here together add up to be 100. Now, if I'm asking myself, what's more popular? And maybe I have, 10 categories. It's a bit hard for me to look at the numbers in the table. If I do it in a visual representation, that might help me see what's going on a little bit more clearly. And that's why we're bringing in a bar chart. This is a bar chart for one-way data. So there's one variable, it's called genre, and it takes on 4 different values: other, drama, comedy, documentation. And by putting in a bar, we can actually see very easily and quickly what is most common. The other category is most common, followed by drama, etc., etc. But the numbers on the side, it can make it still a little bit difficult to understand. Like these numbers are frequency, so I can see, oh yeah, this happened a little bit less than 1,500 times, this one happened a little bit more than 500 times, but maybe I might want to see the percentages instead. Same graph and same height, everything is the same height, the zoom might have changed a little bit, but they're the same height. And here I'm putting the percentage frequencies on the side. So in other, there were 42%. In drama, there was 25%. And I'm taking those numbers from the percentage frequency part of my frequency table. Why is it useful to look at percentage frequencies? Because suddenly I just see that that is at 25%, and I know straight away that drama is accounted for a quarter of the data. So you choose. You can choose which representation you want to do your analysis the best. You might put it in a table, a frequency bar chart, or in a percentage bar chart. Something to note about these bar charts is that there's always a gap in between our bars. And that's going to be different from something we learn a little bit later on called a histogram. A histogram represents numerical data where there's one flowing scale. Here we put a gap between our bars to show that these are separate categories. And there's no real order or connection. We're not saying comedy is better than drama or less or more. They're separate categories within the genre, so we put gaps in between the bars. Got a little summary for you over here. I'm about to give you a question. All right, we're still in the realm of one-way data, but we're now representing it in a different way. We're taking this bar chart that had each value of the variable as separate bars, and we're stacking them. We're stacking them into a segmented bar chart. Let's first understand a little bit about what we're seeing, and then we'll talk a little bit about why. So here is a frequency segmented bar chart. I've taken the frequency of each of the values of the genres, And the height of the segment, like segment is another word for section, shows the frequency. So other had 2,476, so it has a height of 2,476. Then drama is orange, so that's next. And drama was 1,432. So actually the height there is 1,432. If you wanted to work out how high to draw it up, you'd take the previous number, you'd add 1,432, and whatever you get there, it'd be about 3,908. And that's the height there. At the next one, comedy is a height of 1,310, and documentation is a height of 588. Cool, that's how we make it. Why do we do this? We do this because, one, we can sort of see the percentage in the area of the segment. Oh, this bit at the bottom, the other is taking a big part of the bar, so that's a large chunk. The other reason is that we're going to come on in the next chapter and look at two-way data, and we're going to want to compare a few different variables. Here we've just got the one variable, which is the genre. But if I wanted to compare a few things, I could put another segmented bar next to it and another one, and suddenly you can look and compare which has the biggest sections and which one doesn't, and start to draw some conclusions about the data. But most commonly when we do these, we look at percentage segmented bar charts. Same bar chart, same height for each of the segments, but now the y-axis is percentage. So just to briefly show you, the other category was 42%, so we draw it up to 42. Drama was 25, so we add an extra 25. That would take us to about 67 is about the height. 23 would take us to 90. That's 23 in between there. And then there's 10% up there. Having it as percentages makes it a little bit easier to interpret than just having the straight frequencies. The other last point about segmented bar charts is it's important to put a legend over here to show the reader what the segments refer to. Now, if you're drawing one yourself, you won't necessarily be having colors, but you can do your segments like this. You could have one that has lines, and you could have one that has dots, and this can be your bar, and one could just be blank, and then you do a little legend on the side and say, lines refers to TV, and dots refers to something else. If you put in a legend, you will be legendary. Here's a little summary. Let's go to a question. All right, we've seen our data. We've crunched some numbers. We now want to start being able to describe what we're seeing so that later on we can start to do some analysis and draw some conclusions. But let's stick in the realm of describing. We're going to very reasonably often write some reports, and I'm going to give you different ways of writing these reports. Later on, there'll be some cool analyses that we do and some metrics that we talk about, the shape, the center, and the spread. When we're talking about writing a report on one-way categorical data, our main emphasis is just going to be to notice what's going on. And often we'll be asked to talk about these key things when we see data in percentage frequency tables and bar charts. The name of the variable, values the variables can take, the total number of samples, the modal category, and a little comparison of the percentage frequencies. So let's look at that in an example that we've seen before. We're going to be describing the kinds of genres that we've come across in our Netflix titles. Let's go through each of these things. What's the name of our variable? Well, our variable is Netflix genre. It takes on all of these different values. What are the options the variable can take? It can take on other, drama, etc. No dramas. The total number of samples, we can add all these up. We actually calculated it previously. It was 5,806. The modal category, which one happens the most? It is other. And a little comparison of the percentage frequencies, which you'll see in our sample answer. How do we put this all together? We write a nice sentence that brings in each of these ideas. The genres of 5,806 Netflix titles, tick, tick, were other, 42%, drama, 25%, comedy, 23%, and documentation, 10%. That's the options. Those are the values. The modal genre was other with 42%. That's a nice little summary report describing the data that we've seen in this categorical percentage frequency table. Here's a summary of the key ideas from today. I'll see you next time for displaying numerical data. Gimme a mean or a median. Come and learn some data and statistics today. Welcome to the Titanic. All right, we're exploring a little bit more about this data from the Titanic. And I just showed the random selection, but how cool are these people? We've got Queen Elizabeth, Peter Hudson, Helen of Troy, Thor, Achilles, and you know that Iizaki is a cool dude. Today's lesson is displaying numerical data. There are 3 key skills we'll be looking at today: displaying our numerical data with dot plots, with stem plots or stem and leaf plots, and looking at the center, the spread, and the shape. All right, so a dot plot is a way of easily seeing the frequency of your numerical data. And numerical data here is the age of women in the 3rd class of the Titanic. In the dot plots that I'm showing you, I've taken sort of sections of these people in the Titanic. There's 2,000 pieces of data. And while something like a histogram could be useful for showing all the data, a dot plot, you need to count the dots. So I've just taken some sections, and hopefully we can use those to understand what's going on. Here are all the women aged between 15 and 25 who are in the 3rd class. And every single dot is a different person. So you guys are around this age. Who are some of these people? Emily Badman, Anna Turia, Ellen Peterson, Sophie Abraham. These are all real people who were on the Titanic. The dot order isn't relevant. That could have been Sophie or that could have been Sophie. But all of them were 18 years old. And actually, out of all of these, how many? 13 people who were 18 years old, only 6 of them survived. Here's a summary for you to print off if you want to look at some study notes. Let's go to a worked example. I've just taken a bit of a sample here of some of the data. I want to focus on the skill of finding the median. In a future lesson, we'll use this to draw some meaning from the data and try and understand what's going on. Here, we're going to get the skill down pat. How do we find the median? You'll see it summarized a little bit later on, but the position of the median is going to be at the n plus 1 divided by spot of the data set. I'll show what I mean there, but just before we start, n is the total number of dots. So I need to know how many we have. 1, 2, 3, 4, 5, 6, 29. So n is 29, so the position that we want for the median is going to be 29 plus 1 divided by 2. That's 30 divided by 2, which is 15. The median will be the number at the 15th position. So we're going to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That one there is our 15th position. The age is 16. So we say our median age is 16. And what does this represent? It represents the person in the middle of the data set. Half the people were below this number, and half the people were above this number. So if you're saying, well, I've got this group of people, what was there? It's kind of asking what's the average age, but we'll learn a little bit later on about the difference between average and median. But for now, it's what's the median age? Who's the central person in this data set? Oh, they're a person who was 16 years old. Cool, now we're looking at a stem plot or a stem and leaf plot. We like these because they sort of group the data together in bands or in stems that help us summarize it in a clearer kind of way. Instead of having a column of dots for every single number, we've got kind of like a column of dots for every group of numbers, in this case, the tens. And instead of a column, it's a row. So here, all the numbers in this row are between 0 and 10. All the numbers in this row are between 10 and 20. All the ones in this row between 20 and 30, etc. We always put a nice key or a legend to demonstrate what's going on, to say that if we have a number here and a bar and a here, 4 bar 3 is the number 43. You guys have seen this before. You know what's cooking. We always put a title in. We show our data. Let's see if we can find some summary statistics from this stem plot. So the summary statistics we're going to look at now are the statistics about spread. They're the range and the interquartile range. We'll talk a little bit about them later as well. But first, let's learn how to calculate them. The range is the highest value minus the lowest value. So out of all these women in the 3rd class from England, what's the range of the data? How do they spread? Who's the oldest? Who's the youngest? So the oldest age here is 48. And the youngest age is 0. It must have been a baby who was a few years old. So the range of 3rd class British women on the Titanic was 48 years old. Quite a range there, a big spread. But sometimes we don't like to look just at the range because there could be like a really old person. If I added someone in who was 98 years old and they were the only one, the range would be huge, but it doesn't really represent the spread of most of the data. So sometimes we cut away the bits at the end and we look just at the range of the middle section. That's called the interquartile range. And that's calculated by finding the 3rd quartile and subtracting the 1st quartile. What is the 3rd quartile and the 1st quartile? Well, they're the middle of the top half and the middle of the bottom half of the data. What do I mean? Well, first I want to split my data into halves, top half and the bottom half. To do that, we find the median. Back to the median thing. N plus 1 over 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12 plus 1 over 2. It's 13 divided by 2, which is 6.5. So now let's find the position between the 6th and the 7th. 1, 2, 3, 4, 5, 6, 7. That's the 6th spot. That's the 7th spot. The median is halfway in between. It's we've got 18 and 21. The median would be 19.5. I'm going to write that down. But that's not so relevant for me right now. I just need to know that these guys above are my top half of the data, and those guys below are the bottom half of the data. Each of them have 6 data points. Now to find the first quartile and the third quartile, I want to find the median of each of those data sets, right? The Q1 is the median of the first half of the data set. So how do I find the median of the first half of the data set? Well, again, I use my n plus 1 over 2 to find the position. In this case, half the data set has 6 points. So 6 plus 1 over 2, 7, divided by 2 is 3.5. So my Q1 will be halfway between the third and the fourth position. 1, 2, 3, 4. It's going to be here. It's halfway between 10 and 16. 10 plus 16 divided by 2. What's halfway between 10 years old and 16 years old? That's 26 divided by 2. That's 13 years old. And Q3 is going to be halfway between the top half of my data set. Is this making sense? We're repeating the same process a few times, but each time we're doing it, it's kind of meaning a different thing. Halfway the top half. Again, there were 6 data points, so we want to find between the third and the fourth data point. Let's have a look at where they are. 1, 2, 3, 4. It's there. It's halfway between 32 and 33. Now, you don't need a calculation to do that, but you can if you like. 32 plus 33 over 2 is 32.5. So my interquartile range is going to be Q3 minus Q1, which is 32.5 minus 13. Get a calculator, 29.5, and you end up with 19.5. So hopefully that helps you work out how to calculate the range and the interquartile range. Remember, the range uses all your numbers. It includes outliers. The interquartile range is just looking at the middle band. We're trying to see what was the range of ages between here and here. Seeing as we're talking about stem plots, I want to expose you to the different types that you can see. There's 2 interesting parts to this stem plot. We're not going to do an example. I just want you to notice what's going on. So 2 interesting bits. One is the key is a key for decimals. So they're saying when you have a bar in between the 2 numbers, that means a decimal point. For example, this number here represents 3.7. Cool? So you can actually use a stem plot to represent decimals. The other interesting thing you're seeing happening here is that because there are so many numbers, they've actually put each group of 10s over 2 lines. So here you've got all the numbers between 20 and 25, not including 25. And here you've got all the numbers between 25 and 30, not including 30. And that's okay. You're allowed to do that in a stem plot. As long as you're clear and you're consistent, sometimes you will need to split your data over 2 rows. Just keep your rules consistent. So this would have, 5 numbers. This would have 5 numbers. This would have 5 numbers. And this would have 5 numbers. All right, these are the key ideas of a stem plot. Got a question coming up to ask you to calculate that interquartile range. If you need to go back and review what it was, have a look at that and give a go at this next question. All right, we're going to introduce now 3 ideas that we're going to use a number of times over the next few lessons. And these are statistics that help us summarize what's going on in the data. We have the center, we have the spread, and we have the shape. And these are kind of like the headings, the headlines, which we then bring another statistic to support and represent. So when you talk about the center, you might bring the median. Who's the middle person in this data set? You might bring the mean. If I average out everyone, on average, what are these people that I'm looking at? Or the mode, like who's the most common? Each of those values kind of give you a sense of where the data is sitting. What's the center of what we're looking at? We talk about the spread. So when we looked at the age ranges of British women in first class and second class, first class and third class, we actually saw that in third class, the interquartile range was larger than in first class. What does that mean? There's a bigger spread. So if you were one of the most common people in those classes, you were like in your 20s, in third class, there was a bigger spread. It's like you don't have so many people who are the same ages as you. You're trying to find your friends. In first class, the spread was smaller. So there were more people who were kind of around your age. You'll see this in some of the representations we're looking at. Standard deviation is a measure of a spread. We'll come to it later. Skew and outliers are ways that we can describe the shape of data. Let's bring some examples to try and give some concrete visualizations to what we're talking about. All right, let's imagine that you are a manager at a company that takes lots of phone calls. You're working at Telstra and you've got some workers and you really want to improve your customer satisfaction. So you start to take some statistics of maybe different departments. This could be from an entire department or maybe individual workers to see how long are people waiting on the call before they get answered. And we're going to look here a little bit about spread and shape because you're familiar with Center. I can see here there's quite a large spread of the data. People are being answered on their phone calls somewhere between 38 minutes and 0 minutes. I use the range to represent that. I might want to use the interquartile range. And the interquartile range, I just know ahead of time, I've worked this out already, that the third quartile is about 12.5 and the first quartile is about 4. So my interquartile range is 8.5. On average, that's how long it's taking for like the middle 50% of my customers to get their phones answered. Let's compare this to another department at our call center. Ooh, I can see here that we have a different spread of wait times. The range only goes from 1 minute to 14 minutes. It's only a 13-minute range. And our interquartile range, I worked this out beforehand, is 8 for the third quartile and 5 for the first quartile. Our interquartile range is a nice 3. Wow, that's really good. Most of my customers, or half my customers, are being answered within a range of only 3 minutes. It looks to be like that is a better or a really good customer service line. That's spread. What about shape? Well, in my first department, I can see that I have some customers that are being answered pretty quickly. And I sort of then, as I go later on, even though I have large numbers, there aren't too many of them. Whereas in my second department, it's pretty symmetric. So I have, general overall good performance, but I have an equal amount of bad performance and good performance. This one over here is called a positive skew. And this one is called symmetric or approximately symmetric. And as a manager, maybe you actually want your positive skew. Maybe you're like, yeah, I've got some excellent people in my team who get these calls answered in 1 minute. Maybe I really, really like this team because of that reason. Or you might say, I prefer a bit more consistency. Even though on average my wait times are a bit longer, I don't want to have many people really disappointed. I don't mind if only a few people get answered really quickly. I want some consistency. So these are the terms we're going to start to use when we talk about analyzing data. And hopefully you can already see it's going to be really useful when we want to make practical decisions. Remember, our heading here is shape. And one of the descriptors we use for shape is the thing called skew. Skew can be positive, negative, or approximately symmetric. You're very rarely going to find something that's perfectly symmetric. And I've shown here a few examples of skew in different kinds of representations that you're going to see, or different plots. So all of these ones on the left are negative skew. And all of these ones on the right are positive skew. How do you tell when you're looking? I always look for the tail. So here the tail is going to the lower numbers, so that's a negative skew. Here the tail is going to the positive numbers, that's a positive skew. Same here, we're sort of tailing off to the positive. Here we're tailing off to the negative. And for a stem plot, you can look up and down. The tail is going to the lower numbers, so it's negative skew. Whereas here the tail is going to the larger numbers, so that's a positive skew. All right, a wonderful summary slide with all the key takeaways. Just remember, these guys on the left are our negative skew, and these guys on our right are our positive skew. I'll see you next time for displaying numerical data, looking at some histograms. Every night in my dreams, I see you, I feel you. We're back with our famous people, but we've added one tiny bit of information. Whether or not they survived. Unfortunately, Achilles didn't survive, and neither did Thor. Can we understand why? Can we save them? Welcome to today's lesson on displaying numerical data. We're going to be looking at histograms. 3 key skills. Grouped frequency tables. These are the tables from which we make the histograms. And center, spread, and shape are the histograms. I am so happy that we're moving from dot plots to histograms. Do you know how hard it is to make questions with the dot plots? Why is it challenging? Because you need a dot for every point of information. So I could only give you data sets that had just like 20 pieces of data. I had to cut the data here and crop it there and sample it there. And it's just too many dots to count. How can you work with that? We need histograms. Phew. Histograms are your dot plots, but they help you summarize lots and lots of data. When I'm working with data sets that are like 1 million pieces long, like every sale of a house in the US in the past 20 years and all of its features and everything, the only way I can understand it is by showing a histogram. You know, when you say to yourself, oh, why is general maths getting me to draw this histogram? I can see the data. There's 20 numbers. The reality is that when you work with real data, you're working with millions of pieces. You're working with 2,000 Titanic passengers. You're working with 5,000 titles on Netflix. You're working with 1 million houses all across the US. And you need a histogram to be able to actually see and understand the spread of this data. Like I show you here the spread of this data for 2,000 Titanic passengers, and suddenly we can see, oh yeah, it looks like the center is around 2030. It looks like there's a bit of a positive skew. I'm suddenly understanding a little bit about who was on my boat. Nice to meet you. Where you been? I can show you incredible things. A histogram is made from a bin. A bin is an interval of numbers. In a frequency table, a grouped frequency table, which is what we're seeing in front of us, we often call them intervals, 0 to 5, including 0, and that circle bracket means excluding 5. Right? So from 0 to 4.99999. And then here we have all the people who were aged 5 to 10. 5 years, 6 years, 9.5 years, 9 and 9 years. And there were 31 of those people on the Titanic. And for every single interval, we can write the frequency. And that is a grouped frequency table. Why is this useful? It means that we don't have to write a separate entry in a row for every individual number. We're not kind of doing a dot plot, we're grouping our data together. When you see this information in a histogram, it's called a bin. A bin is something you just throw all your stuff into. So we're making a bin for all the people from ages 0 to 5, and there are 51 of them. Look, the bar is at a height of 51. Wow. What about all the people aged from 75 to 80? That's this bin over here, and there's one person there. And a really common group, how about all the 20 to 25-year-olds? Wow, there were more than 175 of them in that bin there. So, what are we doing? A dot plot shows frequency. A frequency table shows frequency. A grouped frequency table groups things into intervals. And a histogram shows those grouped frequencies on a nice display with a bar for each bin. Incredible. If you would like to see all of the bins, I have them here at a nice little table for you. And we have all these wonderful ideas about a grouped frequency table summarized here for your notes. So we've spoken already about histograms and how they come from these grouped frequency tables. I think that was a great explanation, so if you feel like looking back at it again, feel free. Let's point out 2 key ideas. One is that we do have a y-axis in histograms, and that's the frequency, how many things are in each bin. And the other thing to note is that the bars are pushed up right against one another. When we did a bar chart, we had sort of spaces and gaps between the bars to show that we were doing different categories, because we were looking at categorical data. Here with histograms, we're looking at numerical data, so we get a nice flow and no gaps between the bars. So if you were in prison, you'd want to be in a bar chart rather than a histogram, because then you can escape through the gaps between the bars. All right, let's say you're given 1 million pieces of data and you want to be able to see how its distribution looks. You're going to want to create a histogram. Now, when you work with millions of pieces of data, you'll use some advanced software like Python or R or Excel. Here, we're practicing with our calculator to get a sense of how the data connects to the display. So these are the instructions of how to do it on your calculators. Let's give it a practice in the next example. Alrighty, let's see if we can put this data into our calculator and make a histogram from it. On the TI Inspire, we're going to go to Control Doc to get a new page going, and we're going to select Lists and Spreadsheets. If you're on the class pad, go to your menu and press Spreadsheets. Then in this position, we're going to fill in the data that we want to plot. All right, on the TI Inspire, we're going to need to give a name to this column so we can recall it later. So these are the number of skips. So I might say N skips. On the class pad, you've already got a name there. It's like column A. We then want to go Control Doc and Data and Statistics. This is the space where we're going to represent our data. Class pad people, just stick where you are for now. We want to add the data we just made. So we click on the x-axis. That's where our data is going to go. And we click there. Ooh, our data falls into the nice position. We can see we have a dot plot. If we want to make it a histogram, we go a menu, a plot type, and histogram. ClassPad people, highlight the column A where you're in, press graph, press histogram, you'll be on the same spot. Beautiful. All right, here's the histogram, but it's not necessarily showing it in the bins that we want. We can see that in our data, our bins go from 0 to 5, 5 to 10, 15 to 20. There are 1, 2, 3, 4, 5, 6 bins. This data looks to be jumping up in 2s. We're going to need to change the bin width. All right, I want you to hover your mouse over the white space. If you need to, you click on the white space, and you're going to press Control Menu. Control Menu. If it's not coming up, click on the white space. Then you get your bin settings, and we can choose our bin width. We want our width to be 5, and we want to start our first bin at 0. So we go 5, 0. And then we're now getting a good picture of the data we just had. Menu window, zoom data, it zooms out a little bit, and that is the perfect histogram where the height of each bar is the frequency of each of our bins. ClassPad people, press Calc at the top, press bin width, and you can choose the same settings as well. All right, we're bringing in our old friends, center, spread, and shape, and we're going to apply them to a histogram. If you ask for the center, the most common metric to use is median. And if you asked for spread, generally range is pretty good. You could do interquartile range, but it's a bit harder to calculate. You could look at the mode, what's the most common category. But general recommendation, go for median and range. All right, how do I find the median of a histogram? If you wanted to estimate it roughly, you would shade in half the area, because the area here is kind of like the frequency. And, how many times are things happening? So if I wanted to get to half the things happening, I'd sort of shade in equal amounts left and right. I'm not sure, but I imagine our median is going to fall somewhere around here. Let's do it mathematically and analytically and see if we can calculate what it's going to be. Again, the position is always going to be at the nth plus 1th over 2th position. We counted previously, and we said we had 27 people in this data. So 27 plus 1 over 2 is 28. Half of that is 14. We're looking for the number of skips at the 14th position. Here I can say I've had 3 people. If I add an extra 9 people, I'm getting to 12. And that means that the 13th and the 14th person is inside that bar there between 10 and 15 skips. And if you wanted to, you could go the other way as well. 3 people, 8 people, 11 people, and then here we're getting to 15. So again, the 13th and the 14th is between 20 and 25 skips. So that's our median. We don't know exactly because we don't see every single data point, but we can say our median interval is between 20 to 25 skips. All right, how do we find the range of a histogram? Well, we know range is the highest minus the lowest. And remember that in each bin, we don't really know every single data point. Like the binning is a way of summarizing. We don't know whether the highest number in here is 26 or whether the highest number there is 29, right? It could be 29.99999. It could be really high. So what's the highest possible number in this data set? 30. What's the lowest possible number in this data set? 0. Our range is 30 minus 0. Our range is 30 skips. Different histograms can be defined in different ways. Some might include 30 in this bin, some might include 30 in the other bin. Regardless, if your highest number is 29.999999, then that is basically 30. So 29.99999 minus 0 is a size of 30. All right, we spoke about spread, how spread apart is, what's the range of our data. We spoke about center, that was the median. We still need to talk about shape. And shape is a theme you're going to see appearing multiple times. What do? You follow the tail. So Our tail here is going down to the right. It's going towards the positive data. We call this a positive skew. Whereas for this one, our tail is going down to the left. That's a negative skew. Now don't skip ahead for this one because we're starting to get into a bit of an understanding of what was really happening on the Titanic. Who was there? Who survived? All right, I've got here 2 histograms of different groups of people on the Titanic. One of them had a positive skew for the age. One had a symmetric distribution. What do you think this could represent? If I was talking out of the data we've looked at so far on the Titanic, which group do you think would be younger, and which group do you reckon might be a little bit older? The answer is the third class and the first class. The third class had a lot of people who were really young, who got these cheap third-class tickets and went off to adventure and see the world. The first class had these people maybe who brought their entire family, the elderly and the young, and they all paid this lots of money and came aboard together. You know, if you didn't know, if you were trying to do some kind of machine learning model to predict whether someone is a third class or first class, and you didn't know it beforehand, you could look at the shape of the data to help try and understand what's going on and draw these patterns. All right, what about this data? I've taken the variable of the fare, how much someone was charged to buy tickets, and I'm showing you one group of people who tended to pay more for their tickets and another group of people who tended to pay less for their tickets. Now, you might think, third class, first class, we've seen this before. But actually, what if I told you these were people from the same class? Both of these people were first class tickets. Like, these are relatively expensive tickets back in that day. $40, $60, $80. So what could 2 groups be? We're both in the first class, but some bought more expensive and some bought less expensive. We're starting to get into some of the core of the data. The ones who bought the cheaper tickets didn't survive. The ones who bought the more expensive tickets tended to survive. Now you're looking, you're saying, the data looks pretty similar. There's only a slight difference. Well, slight differences in data can mean billions of dollars for these big companies. It can mean the difference between a machine learning model diagnosing an illness or not. It can mean a whole bunch of things. So how do I summarize what's going on? I'm looking at this data. It looks similar. Is one actually more expensive than the other? Well, you could look at the median. The median tells you where the center is. And yeah, the median for this data of the first class passengers who didn't survive was $52. And those who did survive paid $78. So what's going on, right? Why did the people who paid more seem to survive more? Was this happening across the entire Titanic? Yeah, in the second class, the survivors paid $23 as a median, and the median person who didn't survive paid $13. And even in the third class, the median survivor paid $8.50. The median person who didn't survive paid $8. There seems to be a trend going on here. Now, what the reason could be is the next question that you would ask in data science, right? That's a question for the product of your team. It's a question for you as a researcher to answer. Was there better treatment to those who paid more? Were they in positions of the boat that were easier to escape from? Were they able to bribe the officials to get themselves onto a boat? What is the cause of this? Should it mean that we rise up against the capitalists, declare the proletariat as the new leaders of our world, and send the bourgeoisie and the capitalists down to their doom? These are decisions for you to make. I will see you at the revolution. And here we have a nice summary of the key ideas from today's lesson. I'll see you next time when we look at log scale data, and we'll also bring in significant figures there as well for those who are curious about significant figures. Gimme a mean or a median. Come and learn some data and statistics today. Hey everyone, and welcome to today's lesson on log scale histograms and significant figures. Today we'll be using some data from COVID. A histogram is built upon a log scale, so first to understand the log scale histogram, we must learn how to convert to and from a log scale. We'll then interpret these log scale histograms, and we'll also touch on the idea of significant figures, which pops up in a few different places in general maths. Let's say we're sitting in May of 2021, and we're trying to understand different countries' responses to COVID. So we get some data together, and we display in front of us the number of cases per country. So every single individual frequency here is one separate country, and we've put the countries in bins together to count how many countries we have with different numbers of cases. So for example, over here, that's USA in May 2021 had 33 million cases. We've got India here at about 20 million. There's Brazil, there's France, there's Turkey, those are the next sort of 3 in the list at that point in time. Australia at that time had a measly 30,000 cases. So this is 10 million. 30,000 is sitting somewhere over here. And we can say there's lots and lots of countries that only have a few. Is this a useful histogram to help us understand and see what's going on? No, because there's so much data chucked together. And when we're trying to analyze what's happening down the lower end of the scale, the fact that we have all these big numbers really up at the higher end of the scale is throwing our point of view out of whack. We need another method for looking at this data. How do we do it? We do it with a wonderful log scale histogram. Now, I have the exact same data as we had previously, but I've shown it in a different way. You can see that we've changed the x-axis of our histogram graph. And suddenly I can see a distribution. Suddenly, if I can understand what a log scale is, I might be able to actually tell you or interpret what's going on. To give you a little flavor, the USA and India with 33 million and 20 million are sitting there. And actually, every country that had between 10,000 and 100,000 cases is sitting between 4 and 5. So Australia exists somewhere in this bin. All right, let's first learn how to convert the original number to its log scale form. So this 33 million cases in the US or these 30,000 cases in Australia. We're going to take the log with a base 10 of that number. We find the log here, control log. On the class page, you're going to pull up your keyboard. And we're going to put a base of 10 down the bottom. You'll find soon what the connection is to the number 10. And inside the log, with a little arrow to the right, we're going to put the number, the real number. So in this case, 30,000 cases for Australia. 30, 1, 2, 3. And we press enter and we get log base 10 of 30,000 is 4.48. Now let's learn how to convert from a log scale number back to the original one. If we bring up this log scale histogram, you'll remember that I said the USA, which had 33 million cases, was somewhere between the numbers 7 and 8. How would I look at that 7 and 8 and know it had 33 million cases? So we're going to go back and we're going to convert backwards. The way that we do it is we do 10 to the power of the log scale number. So here we go, 10 to the power of, that's that little arrow symbol, up arrow, or in some calculators it's a y to the x, and we put our log scale number in there. If we press enter, we can see that we get 10 million. And if I wanted to know what the number 8 as a log scale number was, we go 10 to the power of 8, we get 100 million. So between 7 and 8, we're actually talking about between 10 million and 100 million. If you weren't getting these numbers on your calculator, go to your settings, check that you've got approximate on rather than auto, and also that your float is just a float and doesn't cut the numbers off for scientific notation. Now you might be starting to spot a bit of a pattern. 10 to the 7 has 7 zeros. 10 to the 8 has 8 zeros. So we can see this playing out in the examples in front of us. The number 1000 has 3 zeros, so in log scale form, it's 3. The number 10,000 has 4 zeros, so in log scale form, it's 4. How do we work with decimals and with negatives? So what we're really doing is we start with the number 1. If the log scale form is a positive, we'll add that many zeros. So 3 will add 3 zeros. But if the number is a negative, we'll start with the number 1. And we're going to move the decimal place that many times. So here, I've got log scale form is -3, and I'm going to move it once, twice, 3 times. And the decimal place is now there, and the number is 0.001. So what would the number -1 be? If the log is a -1, what's the original? Well, I start with the number 1, and I'm going to just move the decimal place once. We have 0.1. You can see that we can actually estimate these log scale values without having to use the calculator. Let's do another one. 10 has how many zeros? It's got 1 zero, so it's there. Which number has 0 zeros? In which number do you move the decimal place no times at all? Well, that's the number 1. Now, you might be saying to yourselves, wow, this is amazing. I never have to use a calculator at all. But all the examples that I've been giving you are all powers of 10, 10, 100, etc. If your number's not exactly a 10 or 100, you do have to use the calculator, but you can estimate what it's going to be. So this number here, 398, we can say to ourselves, it's between 100, which has 2 zeros, and it's between 1,000, which has 3 zeros. So it's going to be somewhere between 2 and 3, because that represents 100, and that represents 1,000. Let's hit that on the calculator. Okay, so I'm just going to do here, log base 10, 398.1. We expected somewhere between 2 and 3. Bada bing, bada boom, 2.5999, 2.6. Are we good with the logs? Are you building a rhythm for your logarithm? All right, log-scaled histograms are really useful when you have data that exists on different scales. And here's an example of that kind of data. If we're looking at the weights of animals or the weights of mammals, we have some mammals that weigh only 0.2 of a kilogram, and we have some mammals that weigh 6,000 kilograms. If you were to show that on a normal histogram, it would be like the COVID data. You would have all these animals grouped in one bar at the bottom, and you'd have like tiny animals at the top. Let's make a log-scaled histogram of that to help understand what's going on. I'll show you how to do it on the calculator, and then I'll ask you to interpret that to see if you're understanding what the log-scaled values mean. We're going to go Control Doc. On the class pad, you go to your spreadsheet. Here we go, listen spreadsheets, and we input our data. All of our techniques are going to be largely the same as making the normal histogram. We're just going to have to make one small change to take the logged values of all of our data. Which silly presenter decided to put 30 pieces of data there? They're all in there now. I counted that there were 30. It was next to the row 30. We need to give a name to our column. Class pad people, you don't have to. These are weights. I'll call it W. All right, now usually we just sketch a histogram like of this, the way I showed you last lesson. We need to do a log histogram. So I'm just going to type in here log W. And that reminds me that these are the values that I've taken the log from. Now I could go in every single line and go, what's the log of 0? What's the log of 0.02? What's the log of 0.02? But that's going to take me a bit of time. Luckily, technology has these wonderful things called formulas, called programs that can repeat an instruction many, many times again. So we go to this little equals row and we type in, I'll do it with a pen, equals. And you can see on the left, it says log W, that's just the name of my column, is going to be equal to what? And I'm going to put here the log base 10 of, what am I taking the log of? I'm taking the log of the W column. Now we're being asked, do we want to choose a column or a variable? We go with variable reference, we press OK, and we get the log of all of these values without having to do any work. How cool is that? Now you'll notice the very first one is undefined because actually you can't take log of 0. If you try that on your calculator, you'll get an undefined value. So when we sketch our histogram, we're actually going to be sketching this without that one data point, and the log of 0 is not a real number. Then, as usual for our histograms, Control Doc, Data and Stats. We add our log values because those are the ones we're making the histogram of. And we change our plot type to histogram. Just like our last lesson, we looked at this with both the TI Inspire and the ClassPad. If we want to match up exactly to what I have on this slide over here, then we hover over the white space, we press Control Menu, and we change our bin settings. We want the width of each bin. I can see in my graph the width is 1, and the bins start at -2. Menu, zoom, data, exactly the same graph. We have here two very significant figures. One of them has been one of the leaders of the Western world, and the other one was a Prime Minister of England. But what are the real two significant figures we have in front of us? Yeah, this 0.000024. So why do we look at significant figures? And is VCA just trying to be mean? No, significant figures are actually a really common tool that we use in scientific research and in experimentation. Let's say that I have a machine that can measure vibrations, tiny vibrations under the Earth's surface. and it measures it to like this level of accuracy. Another way you might have seen this number expressed is 1, 2, 3, 4, 5, 6 is as 2.4 times 10 to the negative 6. When we're like that, we're trying to kind of say, I don't really care about all the zeros beforehand. I just care about these two significant figures. One day my machine might measure 0.000024. Another day it might measure 0.000031. And all that matters to me are those significant figures at the end, because I know that I'm working on this tiny level of accuracy. That's a little bit of the reasoning behind it. Let's see if we can actually understand how to count significant figures. The first key idea is that leading zeros are not significant. That means any zeros at the start of your number and all the way till you get to a non-zero digit don't count. So ignore this, ignore this, ignore this. The number of significant figures I have here is 3. And that demonstrates the second idea as well, that non-zero digits are always significant. All of these 3, the 6, the 8, and the 2, they're significant. All right, any zeros between two significant figures are significant. That's the third point. So the 1 here is a significant figure, the 6 here is a significant figure, and because these two zeros are in between those two, we count them as well. So actually, every digit here is significant. 1, 2, 3, 4, 5, 6. That's 6 significant figures. Let's look at the next ones. Here we have just 3 digits. They're all significant. That's 3. There's another idea that trailing zeros are significant only if a decimal point is included. So here, that's actually only one significant figure. Because what you could be doing in your scientific research is measuring things, and one day you measure it to 100. Let's say you're measuring planes flying past 100 kilometers an hour, whoosh. And then you see another plane, you measure it at 300 kilometers an hour. And you actually know that your measuring device is only accurate to 100. It kind of rounds, so you're only reporting with that one significant figure. Another day you get 200 kilometers per hour. But if you know that your machine is actually quite accurate and it can measure to a very accurate level of detail, and one day you just measured exactly 300, well, then you might report your number like this. You'll say, I got 300.0, which has 4 significant figures. And you put that 0.0 in to say, I actually could measure to that level of accuracy. Just today, it happened to be exactly 300. Now, these last sort of few here, they're a little bit niche. I don't really expect you to come across them. To be honest, this first one is really the main one you want to be used to. And if you want to get your head around number 2 and 3, then you're sailing. Cool. Here's a summary of all the key ideas from today. I'll see you next time for the 5-number summary and box plots. Gimme a mean now or a median. Come and learn some data and statistics today. Hey everyone, and welcome to today's lesson on 5-number summaries and box plots. We're going to dive into our AFL data. Today there shall be 4 key skills. The 5-number summary, using this to draw a box plot. Understanding the upper and lower fences and how outliers are defined. And then the shape, center, and spread of a box plot. 5-number summary. What's the big deal? In my work in data science and machine learning the past few years, I have been using the 5-number summary almost every day. Because, yeah, if VCE gives you a data set of 20 points and they say, do some calculations, 5-number summary, and you're like, why am I doing this? I can see the data. But in the bigger world, when we're working with lots of big data, a 5-number summary is one of the only ways we can understand what's going on. Sometimes we're given a data set of millions of pieces of data. And to understand it, we need these 5-number summaries. We need these box plots. So here I have a data set from King County in the US with 21,000 different houses, very similar to some of the data sets I've worked with previously as well. King County in the US is based in the area of Seattle. Seattle is included in King County. And here we have the real sale prices of the houses and all of their information, bedrooms, bathrooms, the living area, when they were built. And you might be building a machine learning model to try and predict the price of the house based on its features. To understand what's going on, you need a 5-number summary. So let's say I get this data, I get all these prices, and I say, well, what kinds of houses am I looking at? Let's do a 5-number summary to find out. I have all my prices, and now I do a 5-number summary, and I see, oh, cool, the minimum price was $75,000. The maximum price was $7.7 million. But actually, most of the houses, the middle 50% of the data, range between $300,000 and $645,000. So actually, most of the houses I'm looking at are in that price range. And therefore, any machine learning model I build will only really be useful in predicting those kinds of houses, I'm probably going to want to ignore the houses that are super expensive and the houses that are super cheap, or I have to be a little bit more careful and make sure that they're represented properly in my data. So these are the 5 numbers of the 5-number summary: the minimum value, the maximum value, the median, the middle value, the first quartile, and the third quartile. The way that you find this is you follow these instructions on your calculator, and that prints you the 5-number summary. Today we're going to be looking at AFL data and looking at some pretty cool stats there. So here's the instructions. We're going to jump straight into the first question. See if you can use those instructions to find the 5-number summary of the data I'm about to give you. So what is a box plot? A box plot is the connection between the 5-number summary and the visual display. It basically shows us visually what we're trying to see. So soon we're going to show them. I just want to emphasize what these quartiles represent. This 25% is another name we have for Q1. We call it the 25th percentile. And 75% is another name for Q3. It's called the 75th percentile. And you got it. 50% is another name for Q2, or the median. These percentages are actually helpful because they demonstrate what these quartiles represent. Anything below 58 is in the bottom 25% of the data. Anything above Q3 is in the top 25% of the data. And anything in between Q1 and Q3 is in the middle 50% of the data. You'll see that visually soon. The question, let's see how it looks like in a box plot. All right, let's look just at the 2017 data. This is our 5-number summary, and this is the box plot that represents it. The minimum value is on the very left-hand side of the box plot. The maximum value is at the very right-hand side of the box plot. Before we go further, let's remind ourselves what data we're looking at. I looked at Richmond's tackles in 2017, and I counted the tackles the team made in every round. So there are 22 numbers here, each representing the tackles Richmond made in a given round. So the maximum number of tackles, 88. They had a really good game that round. The minimum number of tackles, 50. Maybe it was like a super sunny day and just no one tackled each other. This number in this line in the middle represents the second quartile, or the median. And what we're saying is for half of the rounds that year, the tackles were less than 68.5, and for half of the rounds that year, the tackles Richmond made were above 68.5. This value here is the third quartile. We're saying a quarter of the values were above 77, a quarter of the tackles were below Q1, which is 58. Half of the tackles that Richmond made, like half of the rounds the entire year, Richmond made between 58 tackles and 76 tackles. So we can annotate this and interpret this in many ways. But if you could just note that this box plot shows us the 5-number summary. It shows us the min, the max, Q1, Q2, and Q3. Suddenly we can start to appreciate this as a visual representation of how Richmond performed in that year. For 2015, there's some outliers there. We're going to come to that in a few slides' time. All right, so we know that the left of the box is Q1, the right of the box is Q3, and this value here is our maximum. It happens to be an outlier. What's the end of the whisker over there? To understand the end of the whisker, we need to understand the idea of a fence. In this case, we'll look at the upper fence because we're looking at the top part of the data. A fence is a place you can't fly beyond. If you fly beyond it, you become an outlier. So let's bring it back to Collingwood. We know that one of the games had like 168 marks. The next highest game had about 138 marks. So rough numbers here. Let's say it's 168. What did I say here? 138. Those are two data points from two different rounds. And there was no data in between. But how did I know that this data point should be an outlier and this one shouldn't? So let's imagine we're a little bird. We've got a nice little bird over here. And our mama bird is telling us how far we can fly. Mama bird says you're allowed to fly as far as the distance between Q1 and Q3 times 1.5. I'll give you a little bit of extra room. So our gap here is 92 to 120. Let's just call that gap 30. Mama bird says, I'm going to allow you to fly 30 times 1.5, 45 beyond the third quartile. So from the third quartile here, you can fly as far as an extra 45. 120 would take me to about 165. That's the 45. Little birdie, half your data exists between Q1 and Q3. I'm going to let you fly beyond Q3, but no more than 1.5 times that middle section of the data. Anywhere beyond that point, anywhere beyond that fence is considered an outlier. That's the fence there. We don't draw the fence when we draw a box plot, but it exists in our imagination. Any data beyond that fence, outlier. Any data before that fence, not an outlier. And we draw our whisker up to the previous data point. In this case, 138 marks for Collingwood in that round. Is that making sense? Let's calculate this mathematically and see if we can get a bit more of a feel of what's going on. All right, this is a common kind of question that requires a little bit of workings. We're first going to find the upper and lower fences, and then we're going to decide whether some numbers are outliers or not. Let's consider the upper fence. The upper fence is defined by the third quartile plus 1.5 times the interquartile range. Our little birdie is allowed to fly as far as 1.5 times that distance beyond the third quartile, to around there. Let's see if we can calculate what that is. First, we're going to need the interquartile range. The interquartile range is Q3 minus Q1. And I can see from my 5-number summary, that's 120.75 minus 91.75, which is 29. Okay, that's the gap, that's the distance from my middle 50% of the data. I want to multiply that by 1.5, which is 43.5. You do all this on the calculator, of course. And that's the extra distance, that's the extra gap that I can fly beyond the third quartile. So to work out what that upper fence is, I take my third quartile and I add the 1.5 times the interquartile range, which is 120.75 plus that 43.5. And that gives me 164.25. That's pretty cool. I think in the last slide, I estimated it at about 165. So anywhere beyond that fence there is considered an outlier. I can see that 138 is not an outlier, and 166 is going to be an outlier. But to decide for 69, the lower end of the data, I'm going to need to calculate the lower fence. The lower fence is Q1 minus that distance we're allowed to fly. So Q1 minus the approximate length of 43.5. The nice thing is that I've already calculated the interquartile range. I knew it was 29 from previously. So here I just do 91.75 minus 1.5 times 29. And I get 48.25. So the lower fence is all the way down the bottom, beyond even where I can see the graph. And that makes sense because I don't actually have any outliers on the left side of my box plot. So in conclusion, I'm going to now describe whether or not I have outliers, and I'm going to use the numbers that I've shown. So I'll say 166 is an outlier, and I want to give a reason. It's above the upper fence, which was 164.25. 69 and 138 are not outliers. They are between our fences. They're on the inside. They're between 48.25, which was a lower fence, and 164.25. We're allowed to fly into those zones. All right, we know how to create our box plots, but soon in our next chapter, we're going to start comparing between them. We'll be looking at and doing a proper analysis of Richmond's tackles in 2015 and 2017. And we'll use some statistics to describe what's going on there. You might have already seen a bit of a change between 2015 and 2017, but which words will you use to describe what's going on? Well, you might be asked to discuss the center, the spread, or the shape. Those wonderful ideas we use to analyze our data. And the statistics you use to represent each of these will be our median, our range or our interquartile range, and our skew or our outliers. Those are ones that are very easy and quick to see from a box plot. For example, the mean as a measure of center is a bit hard to see on a box plot, but the median is right there with a line. Now, you've already seen the median. You've seen the spread. You know that's the range is the highest minus the lowest, or the interquartile range is Q3 minus Q1. The thing that we haven't discussed yet is the shape. So let's see if we can look at a box plot and interpret what kind of skew it has. So we know how to find the skew of a histogram. If we can connect a box plot to a histogram, we'll be able to understand the skew of the box plot as well. Remember that the area under the histogram shows the percentage of data that is there. So if I wanted to shade the middle 50% of the histogram, I might be shading roughly these guys over here. And that's the middle 50% of my box plot. And then I've got a quarter of my data there and a quarter of my data there. So the top quartile goes there and the bottom quartile goes to there. If I want to split my histogram into two, I reckon it might go somewhere along there. And that's the middle quarter and the middle quarter of my middle 50%. So we can see that when we have a box plot with a long tail on the left, that's going to be a negative skew. I can do the same for the middle symmetric histogram. I'll shade my middle 50% of the data, and I get a nice box in the middle. And because it's symmetric, the box is also split in half. A quarter of my data goes to the left, and a quarter of my data goes to the right. So when my box plot is balanced, that's a symmetric skew. And I can do the same for the third histogram as well. Middle 50%, last quarter, bottom quarter. We can see the skew can be interpreted also from the box itself. We've got a nice big box on the right, and here's a good friend with our tail on the right, and both represent this idea that the data is trailing off as we're moving to the right, and that is a positive skew. So how do we look at the skew? We look at the direction of the tails, and we look at the direction of that box. If you have a big chunk of the box on the left and a tail on the left, then your skew is to the left. If you have a chunk of the box on the right and a tail to the right, your skew is to the right. It's a positive skew. I'm attaching a link below here to a really great YouTube explanation if you want to dive into this in more detail and understand a little bit more about how these boxes and tails are positioned. But practically, I've looked up through all the past years of VCA to understand what kinds of questions they ask. And what we can see is they very, very often will put the chunk of the box and the tail together. They're going to give you a nice, clear box plot to help you interpret the skew. So over here, nice chunk of a box on the right and a tail on the right, we call this a positive skew. Nice chunk of a box on the left, tail on the left, that's a negative skew. And we get the same thing over here with a positive skew. So yeah, sometimes it can get confusing. What if the box is big and the tail is small? But VCA are going to be pretty clear with you. Notice that if there are outliers, whenever we talk about shape, we talk about outliers as well. Here's a summary. We have a little progress check as well if you'd like to test your knowledge of the chapter so far. See you next time. Gimme a mean or a median. Come and learn some data and statistics today. Welcome everyone to the golden city of San Francisco. Gimme a mean or a median is the perfect description of this lesson because that's what we're going to be looking at. The difference between the mean and the median. Which one is a better measure of center? And if we compare them, can it tell us something about the skew? So the city of San Francisco is considered a pretty liberal and modern city, and it has a bunch of cool laws. One of those is that anyone working for the city will have their salary publicly available and transparent online. If I had to guess, I believe the reason why they've done this is to encourage transparency and encourage equal pay in gender and for people who have similar jobs to be paid the same. What it means for us is that we can have a look at 30,000 people's salaries, their names, their jobs, and how much they're paid. We've got Doug over here. We've got Mr. Wong. Doug's a deputy sheriff. Mr. Wong is a personal trainee. And some of the most common jobs are transit officers, firefighters, and police people. Let's see if we can use this data to understand a little bit about mean and median. All right, let's say I'm trying to do some analysis to understand how much people are paid in San Francisco. Or maybe I'm working in San Francisco and I want to understand how my salary stacks up. So for 20,000 pieces of data, I can't just look at them individually. I need some kind of summary. I print myself a histogram. And the question that I want you to consider as we go through these next few slides is looking at this histogram, what do you think the mean salary is? And what do you think the median salary is? Is there going to be a difference between the two? And to give you a little bit of a feel of what you're looking for, the mean salary would be what you would get if you divided all the money equally between everyone. On average, how much is a person paid? The median salary is saying half the people are getting below this wage and half the people are getting above this wage. I'm trying to find the exact middle. Have a look at this graph and think about where you think the mean might lie and where the median might lie. To help us make a best guess for this question, let's understand how outliers might impact the mean and the median. Let's imagine we have 5 people. One person earns $60K a year, another person earns $80K a year, someone else is earning $40K, someone's earning $20, and someone is earning $100K a year. Nice, clean, round numbers to work with. The median salary here is going to be $60,000, and because it's very symmetric data, the mean is also $60,000. If I added up all the money here and divided it equally between everyone, everyone would get $60,000. What would happen if I changed the $100,000K person's salary to be $500,000? Well, the median's not going to change. The middle salary is still $60,000. Half the people are getting above it, and half the people are getting below it. But the mean is going to change. The mean has been pulled up, because if I added up all the money together and divided it equally between everyone, suddenly everyone here is getting a bit more money. That's the impact of outliers. Is that going to help you understand what's happening with our San Francisco salaries? So I guess the question we have here is, are there outliers in our data? And remember, you don't need to have gaps to have outliers. You can have a very continuous set of data, and there can be outliers. An outlier is defined as if you're above or below the upper or lower fence. How do we find that upper and lower fence? Well, we look at our middle 50% of the data. Let's say a box plot would lie there, and we say we're allowed to fly 1.5 times that distance. So I'm going to take that measure, I'm going to increase it by 50%. Maybe somewhere around here would be our upper fence. So there's actually quite a few outliers in this data. Let's see how close I got. Not bad. Here's the box plot on the data. In this case, because there's just so many data points, the outlier, there's a data point above the fence, there's a data point below the fence, the whisker is going all the way to the outlier. Not always the case. As we saw last lesson, sometimes there is a gap. I'm not showing you the median because I want you to think about what that median is. But what we can see here is there are a bunch of outliers. Do you remember the impact of outliers? If you had to guess now where the mean and the median would be, where might you place it? Aha! So we can see that half the people are earning below $94,000 and half the people are earning above. But if I was to take all the money and divide it equally between everyone, actually everyone would be getting $103,000. And that's the impact of these outliers, of these people who are earning quite a bit. Now, which one of these is a better measure of center? In further maths, we often end up saying that the median is better because it's not affected by outliers. In reality, it kind of depends what you're looking for. If you're the city of San Francisco and you're asking how much were you paying people on average, then you're going to want to know the median because that's kind of how much you're spending per person. But if you are understanding the living conditions of the bulk of the population, maybe you'll want to know the median because you know what half your people are earning above and half your people are earning below. So this brings us into the key ideas that the median is something that is less affected by outliers. If I put some outliers over here, it's going to pull up the mean because we're sort of averaging out all the money, but the median is going to stay the same. And if I make the outliers even further, if I say go further out and then put the outliers up there, the mean's going to jump across. The median would still stay the same as long as it still splits 50% of the data here and 50% of the data there. So when we have outliers, if we don't want to be influenced by them, we do say that the median is the better measure of center. Often if there's a couple of rich people earning some high amount of money, it doesn't actually matter to us as much. I want to know what's happening to the general central person of my city. But if your data is symmetric and there are no outliers, then the mean is just as good a measure of center as the median is. All right, we saw in our previous data that the mean was larger than the median. And we also might notice that this histogram has a positive skew. Is there a connection between that? There is. If you think about the median is what you would get if you shaded in half of your data. So half of my data exists below and half of my data exists above. And when I have a positive skew, I'm sort of spreading that data out over a longer distance. And as those numbers are getting longer and further away, they're sort of becoming outliers, they're becoming bigger, and they're pulling my mean up. So when we have a positive skew, we actually will have our mean being larger than our median. Does that make sense? If you want an interpretation of what the mean is in these graphs, then you think about the balance point. If I had to put a little pivot balance point to balance out my histogram so that it wouldn't tip one way or another, that's the mean. So to summarize that, we have a nice table here that when you have a symmetric data, the mean and the median will be about the same. When you have a positive skew, the mean is further because the data is pulling the mean up. When you have a negative skew, the mean is to the left of the median because the data is pulling the mean down. And that pull can happen either because of general skew, or it can happen because there are outliers that are doing that pull. I'll see you next lesson for describing numerical data. We'll look at writing reports on histograms and box plots. Give me a mean or a median. Come and learn some data and statistics today. Hello, histogram. Wow. How would I describe you? This histogram has a great sense of humor. Now, you could describe a histogram like that on your exam if you like, or you could watch today's lesson and find out how to describe him a bit better. If you do choose to describe him with a great sense of humor, then I will say to you, what you thinking, mate? So today we're going to be looking at writing a report for histograms, for box plots, for dot plots, and I'll give you some examples. Whenever we write a report, we'll often be asked to discuss the center, the spread, or the shape. And when we're asked one of those things, we can choose between any of these options for discussing center, spread, or shape. But some of them will be more useful for different kinds of plots. So I've grayed out some of the ones that we don't really use. Let's think about a box plot. Well, when you're given a box plot, you can see pretty clearly what the median is. That's a great one to discuss. Mean and mode aren't always there. The range and the interval quartile range are also quite readily available, and skew and outliers too. So we might choose these ones that I've ticked when asked to discuss center, spread, and shape. For a dot plot or a stem plot, we get a little dot or a number where each of the data points are. So we can count the median pretty well. We can see the mode. The mean is doable. You could add up all the numbers. You could divide them by the total, and that's fine. So, I'd say median and mode are more common. Mean is okay. I'll give them a little tick as well. Range is pretty good. You take your highest minus your lowest, so that's pretty available. Interquartile range, also okay, but a bit harder to calculate. Standard deviation, not so common. And we can also see skew and outliers pretty well too. When we come to histograms, boom, 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 boom. Well, for the center, none of them are immediately obvious. The median, we know, is sort of like the halfway point of the data. The mean is the balance point that balances everything out. The mode is the most common, and we can say that pretty clearly. But if you wanted to do the mean or the median, you'd have to calculate that from your original data. So I'm going to put all three here because all three might be asked for and are pretty common. But the mode is easier to calculate than the median or the mean. Range is a nice one. You just take your highest point minus your lowest point. Again, if you had the data, you could calculate interquartile range, but why go there if you don't need to? Standard deviation, again, not really so relevant. Skew and outliers, they're pretty clearly visible when you come to them as well. So these are some of the common stats we're going to use in describing center, spread, and shape. I'm going to give you a multiple choice question to test your understanding. Then we'll do some practice report writing using these to really describe what's going on in our plots. All right, here we have a histogram, the number of skips someone is making in 2 hours on Spotify. Just as an example, we have here 11 students were making between 30 to 35 skips, and one student skipped a lot, between 55 and 60. And we're asked to write a report about this histogram to describe what's going on. Specifically, we're asked to address number of students, modal interval, the shape, the center, and the spread. Now, when we talk about shape, center, and spread, we're going to have to choose to use either like the median or the range, and the skew, and we're going to have to name each of those when we quote it. So let me show you an example of the answer. 40 students were asked how many skips they made. That's the number of students Checked. The modal interval was 35 to 40 skips. Check. And now we start to get into this center, spread, and shape. We were asked to discuss the center, and we say the center of the distribution is shown with the median. We're using the word median to describe it. The shape is negatively skewed, and an outlier, because outlier is a part of shape. And the spread is shown with a range of 45 skips. We want to make sure we're using the right terminology here. I'm not saying the spread is 45 skips. I'm saying the range is 45 skips, and that's the way to represent the spread. Just to give you an idea, how do we find the median? We did this in a previous lesson, but to find the median, you need the total number of data, and you go halfway. So just briefly, I'm going to add these up. 1, 3, 7. I'm adding that cumulatively. Plus 11 is 18. Plus 21 is 39. Plus 1 is 40. 40 plus 1 over 2 is 20.5. So the 20th and the 21st data point are between 30 and 40 skips, 35 and 40 skips. And that's why we say the median is between 35 and 40 skips. Let's go on, practice this again using the right terminology to refer to center, spread, and shape. All right, we have here the Bulldogs tackles per round in 2020. In one round, they made 65 tackles. In one round, not so good doggies, only about 36 tackles. Half the rounds had between 47 and 54 tackles. We're asked to write a report about this and specifically discuss the center, spread, and shape of the distribution of data. Now, to be able to answer this, if we have the raw data on our calculator, let's pull it up. We'll pull up a 5-number summary so we can see clearly what our Q1, Q2, and Q3 are. And then we can use them to write a report. You might want to write your report in nice, clear, simple sentences. It might make it easier for you. So, we're asked to discuss the center. And here I'm identifying, this is my point of discussing the center. I have to choose which metric I'm going to use. Mean, median, mode. In a box plot, the median is available. We can see it straight away, 49 tackles. Spread. Well, I could choose the range from top to bottom, or I could choose the interquartile range. In this case, I've chosen the interquartile range, which is the difference between 54 and 47. So the interquartile range is 7 tackles. And the shape, well, we don't include the outliers when we're thinking about shape. I'm just looking at this box. I can see we've got a nice box on the right with a tail to the right. So there's a positive skew, and there are outliers at these 2 points. Notice that I've clearly expressed that I'm addressing center here, spread here, shape here, and then I've named the statistic that I'm using to describe it, median, interquartile range, skew, and outlier. If you want to see the tackling performance in 2021 when they made the grand final, wait for the comparison lesson in Chapter 2. Have you ever had to wait on the phone to the bank or some other organization, and you're just waiting and waiting and they're playing their music? Well, next time you're waiting, maybe you start to think about who's answering a call on the other end. Are they answering it quickly? Are they answering it slowly? Maybe you're a bank manager and you're trying to look at the distribution of your team. How quickly are they answering the calls? So you put a dot plot together of all the data. In one day, someone had to wait 3 minutes. A bunch of people had to wait 7 minutes, and someone had to wait even 12 minutes. Now someone comes along and says, hey, can you write a report on this data? What's happening with the center, spread, and the shape? Maybe later on, like in a chapter 2 or something, you might compare 2 different teams. So I need to discuss the center. What am I going to choose? Dot plot, mean, median, mode. I could go with mode, but median is a common one that's asked. So let's calculate that. There's 20 people. So the position will be 20 plus 1 divided by 2. Half of 21 is 10.5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Halfway between 7 and 7 is 7. So the median is 7. The spread, let's just pick a nice easy one. We'll take the range, which is the top to the bottom. 12 minus 3 is 9. And the shape. Have a look at that shape. What do you think the shape is going to be? We write a report. We clearly address center and we quote the word median with the number. Spread, quoting the word range with the number. And the shape, we say, is approximately symmetric. Nice even shape with no outliers. Even though there's a little gap there, it's not far enough away to be an outlier. So I know I'm drilling this in because I really just want you to be able to get all the marks. Often I like to talk about the understanding and the curiosity of the maths. This is writing a report. It's answering a VCA question. Let's just make sure we use all the right words. When you're asked to write these kinds of reports or to discuss center, shape, and spread, quote the actual numbers you're using and specify the measure or the type of center, shape, or spread that you're using. If you're using the median, use the word median and give the number. If you're using the range, use the word range and give the number as well. You got this. All right, I'll see you next time for 1G and standard deviation. Gimme a mean or a median. Come and learn some data and statistics today. Hi everyone and welcome to today's lesson. Let's say you're running a business and every quarter you make a certain amount of revenue from the product that you sell. Let's say in 1 year you make this amount every quarter. In 1 quarter you make $300,000. Another one, $30,000. Ooh, in the 3rd quarter you're losing 20K. And in the 4th quarter you're losing 20K. Would you like to run this business, or would you like to run this business where every quarter you earn $60,000? Now, if you look at the mean of these two businesses, they're both actually earning on average $60,000 a quarter. But in your first business, it's going to be much harder to run because some quarters you make a lot, some quarters you make a little, and to pay your employees might be a bit challenging. Whereas if you're earning constantly the same every quarter, maybe you have a bit more confidence in your business. If you're seeing the difference between these two businesses, then you're understanding already the difference between a mean and a standard deviation. And that's what today's lesson is all about, understanding this concept of standard deviation. All right, today we're going to look at 3 key skills: an intuition for standard deviation, how to calculate standard deviation using a CAS, and using the standard deviation to compare between 2 different data distributions. Let's say we have 2 different sets of data. Both of them are symmetric, which means they're centered around the mean, they're centered around the median. They both have a mean of 70. If you added up all these numbers, divided it by 5, you get 70, and same with one underneath. They both have a median of 70 as well, but they're a little bit different. I can see on the top, my numbers are much more spread away from the mean, and the one on the bottom have the numbers much more closer to the mean. So if I wanted to describe the difference between these 2 data sets, I couldn't use the mean of them. I couldn't use the median of them, but I could use standard deviation. Now you might challenge me and say, hang on, sir. I know a statistic already that helps me tell the difference between those 2 things. It's called the range. Clearly the range of the top is bigger than the range of the bottom. Why do I need standard deviation? Let me add a number, just so I can have some more data to play with. And it's the same idea at the top. Top one, bigger spread than the bottom one. And let's change it. Let's change this bottom one to be 100 and this bottom one to be 40. Suddenly, the range of these 2 data sets are exactly the same, but there's still a difference between the 2 data sets. So if I looked at the mean, the median, and the range of these 2 data sets, they would all be identically the same, and they wouldn't tell me that this bottom one has a much smaller spread. I need that standard deviation. Then you say, hang on, we have something called the interquartile range. And the interquartile range of these 2 data sets will be different. So what do we need the standard deviation for? Okay, let's take 2 data sets exactly the same. Same mean, same median, same range, same interquartile range. That's our Q1, that's our Q3. If I was to come along and change some of these numbers, let's say these ones, I'll make this one 69, 68, 67, 71, 72, 73. Suddenly, I haven't done anything to the interquartile range or the median, but the spread of my data is different. Suddenly, the second data set is much closer to the mean than the one above. The mean of these data sets is still 70, right? But the one below have the numbers much closer to the mean than the one above. The standard deviation is what we're looking for here because it describes the spread of every single number in the data set from the mean. Just as an example, this number 60 is 10 away. This 50 is 20 away, and this 40 is 30 away. This 69 is 1 away, this guy is 2 away, this guy is 3 away. That's what standard deviation is going to be able to capture. It's going to be able to capture the fact that these numbers are much closer than these numbers. And it very much uses this idea of how far away is every single number from the mean. And that's a great way to start thinking about the standard deviation. The standard deviation represents the average distance of each data point from the mean. So let me give you an example. I'm making up another data set. Let's say we have a data set with these numbers, 5, 10, 20, 35, and 5, okay? The total there is 40. If we divide it by 4, the average is 10. So that's my mean. If I want to start to calculate the standard deviation, I would say how far away is each data point from the mean? So 5 is 5 away from the mean, because the mean is 10. These are my distances. 10 is 0 away, 20 is 10 away, and 5 is 5 away. What's the average distance of my data points from the mean? 10 total is 20, divided by 4 is 5. I could say, on average, each of my data points is a distance of 5 away from the mean. And that is a statistic that captures the distance of every single data point. So every data point is coming in and contributing towards this value. You don't have to understand how we do this, because we're basically going to just do it on the calculator. But hopefully this gives you a bit of an intuition of where the standard deviation comes from. This number 5 is not the exact standard deviation. There's a little bit more to the calculation, which is far beyond this course. So don't worry about that. Note that you're not going to get exactly 5. But if you understand where this number 5 comes from, then you're basically understanding the key principle behind standard deviation. Does that make sense? If it does, great. If it was a little bit confusing, that's okay, don't worry. It's beyond the course, what we just looked at just in this little slide here. In a few minutes' time, we're going to use the calculator, and you'll be able to solve it all there yourself. But before we do the calculator, I just want to check your understanding of the ideas so far to see if you understand the general principle. And I've added one keynote here, which makes sense from what we've seen. That because our standard deviation looks at the distance of every single number from the mean, it's going to be affected by outliers and skew. If I have a really big number that's very far away from the mean, an outlier, that's going to impact my standard deviation. Does that make sense? All right, in a moment, we're about to see the standard deviation on the calculator. And there are two little symbols that both mean standard deviation. One is an S, and one is a sigma. It's a Greek letter called sigma. Just as a fun fact, if you've seen this letter, Greek letter, that's also called a sigma. That's the capital sigma. And the one that we look at is the lowercase sigma. Anyway, you actually don't need to worry about sigma at all, because in further maths, we just look at S. It's the difference between taking a sample from a population, like sampling everyone in Australia. When we do the census, we sample everyone in Australia. Whereas often when we do research, we don't have enough resources to ask everyone. We just take 10,000 people or 1,000 people. And whenever we do that kind of sampling, we always use an S. In general maths, we always do that kind of sampling, where we research a sample of the entire population. So we're always using S, and that's the only letter you have to worry about. All right, in practice, all we ever really need to do is take a bunch of data, calculate the standard deviation. On our TI Inspire, we're going to make a new doc, our lists and spreadsheets, and we'll put our data into the calculator. I'm going to calculate the standard deviation of the top row, and then just show you how it changes when we change a few numbers for the bottom row. If you're on the class pad, then you want to go to your main menu, go to spreadsheet, and put the data into a spreadsheet just like I'm putting it into it over here. All right, on TI Inspire, we need to give it a name. I'm going to call it D for data. And now we want to show the one variable statistics. It's one variable's worth of data. And in those one variable statistics, we'll find the standard deviation. If you're on the class pad, you want to just highlight the column, highlight the A, and then go calc and one variable statistics. For our TI Inspire, let's go a menu. We want some statistics. We want some stat calculations, and we want it for one variable. There's just one list. We put in our X1 list the name, so in this case, D. First result column, that's just saying where we're going to print it, because it's going to be printed in the spreadsheet. And we'll press OK. And we have over here all of our one variable statistics. You can see that we've sort of printed it to the right of column D. So that's our original data on the left. And we actually get a nice print of all these ones down here. We can see we have sigma, which is the population standard deviation, and we have S, which is our standard deviation that we want. So in here we have 47.61. We're going to do two things. I'm going to show you how to calculate it in a different way on the TI Inspire. And I'm also going to change two numbers to see if we can predict what's going to happen. I'm going to take two of our numbers, our 10 and our 20, and I'm going to make them closer to the mean. 28, 29. And I'm also going to go down to 130 and make that one closer to the mean, and also make that one closer to the mean. Now, how should that affect our standard deviation? Do you think it's going to go up or is it going to go down? Let's see. I'm going to show you the other way of calculating it. Control Doc, Calculator, a menu, Statistics, Stat Calcs. Again, one variable statistics. Same as before. The name of the variable has not changed. And we press OK. Where are you? Aha! Our standard deviation is now 43.32. As we predicted, the numbers are closer to the mean, so our standard deviation has decreased. All right, so we have a measure of center, which is the mean. And we've now learned this new idea called the standard deviation, and that's the measure of spread. Mean tells you where the center lies. The spread, the standard deviation, tells you how far away the numbers are from that mean. Can you use that understanding to answer this question? Cool, and that is an intuition for the standard deviation. Hopefully when you come across it in the future, you've got a bit more of an understanding of what it means. The standard deviation represents how spread the data points are from the mean, and it's going to be affected by things like the outliers and skew. Remember, the letter that we're looking for in the calculator is that lovely little s. I'll see you next time for jumping into the normal distribution. Look, there it goes, that curve is so peculiar. I wonder if I'm feeling well, with a dreamy far-off look, and my nose stuck in a book. What a puzzle to us general maths is bell curve. Welcome to today's lesson on the normal distribution, the bell curve. 3 key skills. The normal distribution. What is it? Where does it come from? Who are ya? The 68, 95, 99.7% rule. And then converting percentages to amounts, a specific skill that often comes up. So many teachers will tell you that everything in the world is normally distributed. And many things in the world are normally distributed. I've got a few examples for you here. But the reality is that lots of things are not. And as you go further in your statistics learning, if you take it into university, then you'll learn different kinds of distributions. But the normal distribution is like the first one that we learn because it's one of the most common ones. It does pop up all over the place. And it's cool to understand because the mean and the median are identical and the curve is very symmetric. We have here a nice symmetric kind of curve. What's this? It's the minimum temperatures in London in 2020. So I took the temperatures of every day of the year, plotted them on a histogram. Which ones happened the most? Yeah, the most common one was about 9 degrees. 20 degrees happened as a minimum temperature, but it was rare. And -4, -5 degrees happened, but they were also pretty rare as well. So we get this nice symmetric curve. Another thing that is normally distributed is heights. So I think I took this data, or at least the parameters for this data from the Australian Bureau of Statistics. The average height of Australian women, around about 160. And there's a certain spread as well that tells us how far we often go. What else is normally distributed? If you're into agriculture, and you're analyzing fruit, or you're a researcher, you're trying to understand the impact of climate change or pesticides or a new growing technique on your fruit, you might look at all the apples that you've made in a certain area, and you can look at their distribution. And the weight of apples is also normally distributed. We start to get here to data that is a little bit less normally distributed. This is the average disposals of plays in the AFL in 2021. Across all the plays, on average, they seem to average about, well, their centre was about sort of 13, 14, 15, 16 disposals. We had a bunch of plays that had many disposals and also a few plays that had some small disposals. This is not a perfectly normally distributed curve. There is a bit of a positive skew towards the right. And so there's a question of whether we can use normal techniques to analyze this. We might say it's approximately normal, and so we can approximately use our normal techniques. But if you go further forward in statistics, you might learn your other distributions that you could use to analyze skewed curves. When we move into normal distributions, we start to talk about a curve rather than an individual histogram. So if you remember, a histogram had these bins where we look at how much data we have, we put them into bins, and we count the frequencies. So this bin here is 150 to, how wide is each bin here? Maybe it's 1, maybe it's 2. Let's say it's 1. 150 to 151 grams. And the height of that bin is the frequency. So we say we had about 90 apples that had a weight between 150 and 151 grams. When we jump over to curves, we're changing a few small things. We're basically drawing a curve over the histogram, but we're going to start to talk about percentages rather than frequencies. Sort of the entire curve will represent 100% of our data, kind of like all of our apples. We'll go into that in a little bit more detail soon. So the shape of this curve is where the name comes from. It's why we call it a bell curve. And it took me about till I was aged, 25, until I realized it. I think I was driving down from a swimming pool, Harold Holt, one day, and I was just driving along and I was like, bell curve. Why is it called a bell curve? And then the picture of a bell came to my mind. I'm like, oh, this is a bell if you ring it. I don't know how you can ring it. But anyway, that's why it's called a bell. It looks like a bell. Boom, mind blown. At least mine was. We define our bell curve with two parameters. We talk about the mean, so 150 grams, where is the center of this curve? And we talk about the standard deviation, which we looked at in our last lesson. So if you have a large standard deviation, you'll be very spread out. Ooh. And if you have a small standard deviation, you'll be very tight and squashed in. Those two curves have the same mean, just different standard deviations. And what did I say? The area under the curve is always 100%. So if I shaded all of this, I get 100%. This guy is also 100%, and so too this one over here. All right, let's dive into this normal distribution curve a little bit more and see if we can understand the connection between the standard deviation and the percentage under the curve. I said beforehand that under the curve we have 100% of our data. And in fact, this curve goes on forever. It just happens to be that there's not much under those little tails. So it kind of makes sense that if you can cover all of your numbers, you will have all of your data represented under the curve. Because the curve is symmetric, it means that we'll get 50% of the data to the right of the mean, to the right of that center, and we'll also get 50% of our data to the left. But if we want to go into a little bit more detail, we have to start to think about and understand the connection between the standard deviation. By the definition of a normal distribution curve, 68% of the data will lie within one standard deviation of the mean. So one standard deviation is down to there and up to there. And I'm telling you that 68% of the data lies in that zone. Let's put some numbers to this just to make it a bit more understandable. Let's say we're talking about our Fuji apples. And the mean weight was 150 grams. And the standard deviation of that data set, the data set was analyzed, the standard deviation was calculated. The standard deviation was 5 grams. So we go down to 145 grams and up to 155 grams. If I picked a whole bunch of apples from all of these trees, 68%, almost 70% of all those apples would have a weight in this zone. Now you might say, well, how is that possible? Well, first of all, it's not exactly 68%. There is a decimal in there. But that number is still the same every time. You say, well, not all the data in the world follows this pattern. And that's true. But if it follows this pattern, then we call it a normal distribution. And if it's close, we can call it approximately normal, and we can still do these calculations. You'll often see in the VCA questions, they talk about approximately how many, because these values are approximate. If you didn't follow this rule, if within one standard deviation you had 80% of the data or 50% of the data, you'd be talking about a different distribution. When there are other ones, there's the T distribution, and there's a whole bunch. But for normal distribution, if you're told the data is normally distributed, then you know this as a fact. 68% will be within one standard deviation. And if we go further, if we say to two standard deviations, so 140 to 160, well, that's going to have 95% of your data. So almost all your data will lie within 2 standard deviations of the mean. Most of your apples will be in that zone. And if you go to 3 standard deviations, so what's another 5? Well, that's 165 grams down to 135 grams. Well, you'd have almost all of your data. 99.7% of all of the apples you pick from these trees will lie between 135 to 165 grams. How do you like them apples? So we have these percentages. We want to remember them. 68, 95, 99.7. But we're not always going to be asked these nice questions of what percentage lies between 1, 2, and 3 standard deviations. We might be asked to find what percentage lies in this area here between 1 standard deviation above the mean and 2 standard deviations above the mean. In terms of apples, that would be what percentage of apples lie between 155 grams and 160 grams. That's a legitimate question you might ask if you were doing research on these apple trees. We can use our 68, 95, and 99.7 to uncover the percentage that should lie in there. Let's do it a little bit like this. I know that within 2 standard deviations, I will have 95%. That means that in this zone here, I'm going to have half of that, half of 95%. So 47.5 is going to lie in that blue area that I just shaded. But I want to hone in on just that area between 1 standard deviation and 2 standard deviations. So let's use this 68% understanding. If 68% is plus 1 standard deviation or minus 1 standard deviation, then in this orange area, I'm going to have half of 68%, which is 34%. So to work out the percentage that lies in my nice green zone, I'm going to take my 47.5, which was that entire area above the mean. I'm going to get rid of the orange bit, which was 34, and I will see that I have 13.5% lying inside that zone there. So if someone asked me what percentage of apples are between 155 to 160 grams, I would say 13.5%. And you can do these calculations to actually uncover the area of any individual segment under that normal distribution curve. I'd like you to practice this and to get used to it, because you might need to be a bit flexible in terms of the question given to you, but I am going to give you a summary of all these on the next slide. So here's a nice summary. I've basically gone through all the calculations for you, or someone on the internet has, and I realized they were wrong and I had to update them to make sure they were right. Edrolo have made this lovely graph, which you can print off and put in your notes, which basically tells you what we just found out, that between 1 and 2 standard deviations, you have 13.5%. Up to 1 standard deviation above the mean, there's 34%. And your little tail here, well, between 2 and 3 standard deviations, you get 2.35%. What's this 0.15% doing? I'll just show you where it comes from. We said between 3 standard deviations, there was 99.7% of the data. That means that there's still 0.3% of the data that exists beyond 3 standard deviations. So if I do 100 minus 99.7, that gives me 0.3%. We're still in the world of percentages. That is above 3 standard deviations and below 3 standard deviations. But everything is always symmetrical, so I need to halve that to get my 0.15. A half of 0.3% is 0.15%. So actually above 3 standard deviations, above 165 grams, I've still got 0.15% of the data. And below 3 standard deviations, below 135 grams, I've still got 0.15% of the data. Some people get confused when we look at decimals with percentages. So this is a percent. If I wanted to make it into a decimal, I would divide it by 100 and it would be 0.0015. That's the same thing as 0.15%. So a few percentages there, a few summaries. This is a really nice picture to put into your notes and use it to call upon when you're trying to calculate the percentage of your data that lies within certain standard deviations. Here's a nice summary, and a key tip from me is that whenever you have any of these questions, do a little sketcheroo for yourself, put down where the mean is, and ask yourself, am I trying to find between 1, 2, 3 standard deviations? That image will really help you identify what you're trying to find. So we know how to calculate the percentages that lie within certain standard deviations, but what if we wanted to know the number, like the actual amount of the data? Yeah, you're doing your research and you say 81.5% of the apples lie between 135 grams and 160 grams. But what if you're Farmer Sam and you want to know, how many apples? Do I have 1,000 apples? Do I have 2 apples? How many apples do I have to eat? So we're going to now work out how to do that. Let's say I have 2,000 apples. And I've just worked out that 81.5% of the apples lie between here and here. What was that, 140 and 155 grams. How many apples will I have? Oh, well, I want to find 81.5% of 2,000. If you know it, bang, go to the next slide. If you're not sure how to do that, let me give you a reminder. And what I love to do when I explain this is to use the words that we actually say. 81.5%. So I'm going to write down what I say. 81.5 per. What does the word per mean? It means divide, like kilometers per hour. This many cakes per people. We're dividing. So per means divide symbol. Percent. What does cent mean? Century, cents means 100. So percent literally means divide by 100. 81.5% of, in maths, the word of, it always means times. So of 2,000. So if someone comes along and says, calculate for me 81.5% of 2,000, you should go 81.5, write it down. Per is divide. Cent means 100, write it down. Of means times. Bang, and that's the calculation that you need. All right, so we have here our Uber Eats. The mean is 20 minutes. We're asking for how many are between 5 and 10. So 15, 10, and 5. We're asking for the percentage between 3 standard deviations below and 2 standard deviations below. We jump across to our lovely notes and we can see that that is 2.35%. So I know that 2.35% of my deliveries will be between 5 and 10 minutes. If I've done 700 deliveries, then I want to find 2.35% of 700. 2.35 per means divide, cent means 100, times is of 700. 2.35 divided by 100 times 700, put it into the calculator, 16.45. Obviously, do it in the calculator, do what works for you. A question like this would often tell you to round it to the nearest number. So let's actually pretend the question's asked that. We've been asked to round to the nearest number of deliveries. So our final answer would be 16 deliveries. All right, here's a summary of all the key ideas for the normal distribution. Next lesson is z-scores, which is very connected to the normal distribution. And we use z-scores to compare between two different normal distributions that have different means and standard deviations. See you then.
Bonjour, AFL data, and welcome to our lesson on z-scores.
A key question guiding us today is, in a certain game in 2018, St Kilda scored 120 points. And in a certain game in 2020, St Kilda scored 100 points. Our key question is, in which of those games was St Kilda the better attacking team? To answer this question, we will use z-scores. And in our exploration, we will cover two key skills. The first will be finding a z-score. And then, once we have a z-score, what if we wanted to go back and find out what the original data was? Okay, so you look at this data and you say, hang on, 120 points, better than 100 points. That game of St Kilda's in 2018 must be better or more attacking than their game in 2020. Bang, lesson done, see you later. Unless there's more to it. In 2018, the average score of teams was around about 75. In 2020, the average score of teams was round about, I'm doing this roughly, 60. So teams were more attacking in 2018 than they were in 2020. Meaning if you get a score of 120 in 2018, maybe that was just easy to do. Maybe defenses were less. Maybe getting a score of 100 in 2020 was actually pretty hard and puts you right up there in the top echelon of attacking teams. Why is 2020 less than 2018? It could be a difference in style of play, but if you remember, that was the year of COVID when they shortened the quarters down to be much smaller and teams tended to score less points. Now, this curve here is not fully normally distributed. It's approximately, it's kind of not really normal, but we're going to treat it as normal because it's close enough for our analyses and to demonstrate our ideas. So from here on in, we're imagining two normally distributed curves, one with the mean of 80 and the other one with the mean of 60. And I actually calculated this from the data. So I know last slide I said 75. That was just me estimating from the histogram. The mean of that data was 80 and its standard deviation was 25. The mean of this data in 2020 was 60 and the standard deviation was 20. So using that understanding of this standard deviation, we're going to answer and hone in on whether the 2020 score was or was not more attacking than the 2018 score. Which score was rarer? Which was a better attacking score for that year? And I'll remind you that the further you are away from your mean, the smaller the percentage, the smaller the chance you are of getting that score. So for 2018, if our mean was 80, then it's harder to get a score of 100 than 80, and it's even harder to get a score of 120, it's even harder to get a score of 140. We're kind of counting how far are we walking away from the mean. And one way to measure how far you've walked away from the mean is to say how many standard deviations are you. So let's look at this score of 120 points in 2018. Our mean is 80, and our standard deviation is 25. So one standard deviation would be over here at 105, and two standard deviations would be another 25 away. It would be over here at 130. Therefore, our score of 120 points, well, it's somewhere between one standard deviation and two standard deviations away. Whereas if we look at 2020, our mean there was 60, and our standard deviation was 20. So one standard deviation away is 80, two standard deviations away is 100, and that is our score over there. St Kilda's score of 100 in 2020 was exactly two standard deviations away from the mean. And if you look at these curves, if you look at the area underneath, you can see that the percentage here is larger than the percentage here. Because the more standard deviations you are away from the mean, the smaller the chance you have of getting that score. It looks like that in 2020, that score of 100 points was much rarer, was much harder to get, and therefore that game of St Kilda's seemed to be a better attacking game. Let's see if we can put some numbers to this measure of how many standard deviations we are away from the mean. So for the top one, if I want to know how many standard deviations away 120 is from the mean, well, I'd do my 120 and I'd say, how far away are you from the mean? 120 minus 80, you're 40 away. We'll say, well, a distance of 40, how many standard deviations is that? I'll take my 40, we divide it by 25, that's the one standard deviation, and if you put that in the calculator, you'll get 1.6. This number here is exactly 1.6 standard deviations away from the mean. To do the same thing with our 2020 scores, we'll take our score of 100, we'll say, how far away are you from your mean? You're, in this case, also 40 away from your mean. But how many standard deviations is that? 40 divided by one standard deviation, that's 2 standard deviations away. I can see that this number, or the value that gave me this z-score, is a rarer value than the one that gave me 1.6. All right, I just used that word z-score. What does z-score mean? A z-score is literally what we just calculated. A z-score is how many standard deviations are you away from your mean. What do I mean? Sometimes we'll draw our original data and we'll say, oh yeah, the mean was 60 and we had up to 140 down to there. And sometimes we'll say, I want to represent this in terms of the z-scores. I'm going to translate this data down to represent how many standard deviations each value is away from the mean. So here the number 100 literally means 2 standard deviations above the mean. The number 140 literally means 4 standard deviations above from the mean. And I can go backwards as well. I can say the number 20, you are 2 standard deviations below the mean. So if you're confused about what z-scores are, you really just need this graph over here. A z-score is a number that tells you how many standard deviations you are from the mean. And when you draw the graph of all the z-scores, you're translating the original numbers down to each of the distances from the mean. The number 60 is the average. So how far is 60 away from the mean? Well, it's exactly bang on. So it is 0 standard deviations away from the mean. So a z-score will, or the distribution of the z-scores will always have a mean of 0. They'll all be centered around 0. And they'll have a standard deviation of 1, because each step is 1 standard deviation, that's another one, and that's another one. All right, so we've spoken about the theory and understanding of what these z-scores are and where they come from, but we want to talk practice. We want to talk formulas. How do we actually do this? How do I take this number 140 and convert 140 into the number 4? I hinted at this previously. I said you take your number, which 140. First you work out how far away it is from your mean, which was 60. And then you divide it by the length of one standard deviation. In this case 20, and that gave you 140 minus 60 is 80, divided by 20 is 4. That calculation we just did is the formula that you get shown when you look at the formula for a z-score. Let's break it down into some symbols so we can recognize those symbols a bit later. Well, 140 is our x value. We say x is like all the numbers that this variable can take. X is like all the possible scores the team can make in 2020. We minus the mean, like the average score that was done, and we divide it by the standard deviation, which was our 20. So that's all we have. X is our actual score. X bar is our mean. And S is our standard deviation. In this case, it was 20. Is that formula making sense? All it is how far away are we from the mean, divided by what's the size of one standard deviation. So then we calculate those Z-scores for different data, and that allows us to compare. For example, we found out that in 2018, St Kilda's game of 120 points was 1.6 standard deviations above the mean, and St Kilda's game in 2020 was 2 standard deviations above the mean. And putting it on one nice Z-curve actually helps us see which one was more likely to occur than the other one. All right, those are all the key ideas you need for understanding Z-scores. We've got the formula over here. We've got the memory that it's just counting how many standard deviations are you above or below the mean. Let's now put it into practice so you can get a bit of confidence and a bit of a feel of how it works. All right, so we know how to find a Z-score from the original score. But what if we want to go backwards? What if we're given 2 Z-scores and we want to find what the original score was? Well, we have a formula that connects x, our original score, and z, our standardized score. And if we play with this formula, we might be able to put it into a different form. Let's do a bit of algebra to work out what the new formula should be. Then I'll give it to you and you can use it without doing the algebra. So I've got my z score is my original score minus the mean divided by the standard deviation, and I want to get the x by itself. So we'll times both sides by s. Z times s is x minus the mean. Now I still want to get this one by himself, so I'm going to move that mean over to the other side. I'll plus both sides by the mean, and we get z times s plus the mean equals x. The order when you plus things doesn't matter, so I can write it like this. I can write the mean plus z times s is x. And then if I want to put the x by itself, I can say the x is the mean plus the standardized score multiplied by the size of one standard deviation. And we see here that that is our formula, which we're going to use now a few times to go from the standardized score back to the original score. All right, the height of Australian adult women is normally distributed with a mean of 162 centimeters and a standard deviation of 7 centimeters. Going to do a nice little bell curve. 162. If I went up 1 standard deviation, I'd get to 169. If I went up 2 standard deviations, I'd get up to 176. We're given a z-score. So we're given a number on this curve down here, which is the distribution of all the different standardized scores. We know that they have a mean of 0, and they go up in ones, 1, 2, 3 for 3 standard deviations, and down in ones, -1, -2, -3. In that way. We're told that Lisa's standardized height is -1.5. So Lisa's height is here. She is 1.5 standard deviations below the mean. Now, if you wanted to, you could just calculate it sort of without any formula. You could say, well, I'm going 1.5 standard deviations below the mean. So 1 standard deviation below 162 is 155. I've taken away 7. And then 2 standard deviations below that is 148, and Lisa's height is 1.5, so she'll have to be exactly halfway in between there. Now you might calculate it, you might know what that is, and you've got the question, but I want to show you with a formula because sometimes the numbers won't be nice and easy, sometimes the decimals we'll have to round, so let's make sure that we know how to use the formula. We said before the formula for the original score in terms of the standardized score was x equals the mean plus z times the standard deviation. So this score, this original score that we're looking for, that's our x score, is going to be a mean, which is 162, plus z was -1.5 times 1 standard deviation, which is 7. And you can see that this formula is actually doing the exact thing we did when we moved down from 162, 1.5 standard deviations. We start at 162, then we go down minus 1.5 times 7. Does that make sense? Like the maths always matches up to the logic. In this case, we put that into the calculator, 162 minus 1.5 times 7, and we get 151.5. So for a standardized height of -1.5, the actual original height is 151.5 centimeters. All right, to bring this all together, let's use z-scores as they were intended to help us compare between 2 different distributions. We have a crop of Fuji apples, which is our A crop, and we have another crop, which is our B crop. Read the question, give it a go, we'll solve it on the next slide. Okay, our A crop has a mean of 155 grams. Our B crop has a mean of 150 grams. The A goes up in 7s, 162, 169. The B crop goes up in 5s, 155, 160. To the nearest gram, what apple weight from crop B would have the same standardized score as an apple from crop A that weighs 160? So I'm looking at crop A, an apple that weighs 160. I can see it's between 0 and 1 standard deviation. Let's find out that z-score. We use our z formula. Z equals the number, which is 160, minus the mean, divided by the standard deviation of 7. 0.7 0.7143. I'm going to use a bunch of decimal places so that I, only do the rounding at the very end. All right, this z-score of 0.7143, what weight would that represent in crop B? Which weight from crop B is exactly 0.7143 standard deviations above its mean? So it's going to be somewhere over here. And I can see already that it's going to be between 150, 100, and 155, and it's going to be closer to 155. Let's use the formula for that one to go backwards from a z-score. The original score in crop B will equal our mean plus our z-score times our standard deviation. In this case, our crop B mean is 150. The z-score we're looking for is 0.7143. We multiply it by the standard deviation of B, which is 5 grams. On my calculator, I don't even need a round. I can just take all the decimals, press enter, and I get 153.5714 to the nearest gram. The answer is D. If you can understand that question, then you are acing your understanding of z-scores. But ultimately with z-scores, there's only really 2 formulas you ever need to know. How to find a z-score, and how to find the original score if you have a z-score. That's our end of chapter 2. It's a progress check coming up and a topic test which you can use to assess your understanding. I'll see you next time for chapter 3.